Um, Previously, we went through how to characterize series solutions to differential equations, at least for our second order homogeneous differential equation. I put it in terms of these decision tables. If we're going to center our solutions, our series around zero. So we're looking for a zero, an ordinary point, regular singular, or irregular singular. And if it is a regular singular point, then we're in Frobenius territory, and we can further characterize things from the initial roots. Briefly go over some of that. Here was how we compute the initial roots. Starts before. We solve this quadratic equation, and we get this A0 and B0 from the P and Q of the standard form. So we have a formula for finding our initial roots. We have three cases of possible Frobenius series. And we have this decision table. So with all that, let's get into some examples of applying all that. Here's our first example, x y double prime plus y prime plus 10y equals 0. Standard form, you can see that p is 1 over x and the q is 10 over x. So this a sub 0, if I multiply this by x, I get 1. A sub 0 is 1. If I multiply q by x squared, I get 10x. X equals 0, that's 0. So b sub 0 is 0. Put those into this equation. Do this. 0 is 1 and 0 is 0. This is r squared minus r plus r, which is just r squared. That equals 0, which means the two roots are 0. R1 equals R2 equals 0. That is a case 3 case. That's where initial roots differ by the integer 0. That's the case in which you're only going to get one linearly independent Frobenius series solution. And because that's the only singular point, the radius of convergence is infinity and the IC is 0 to infinity. Exactly one Frobenius series solution. Others in the linearly independent solution will involve that natural log of x, and we're not dealing with that in my course. So let's look at this second example. Here it's already in standard form for us. Singular points are 0 and 1. 1 is irregular, but it doesn't matter. 0 is a regular singular point. P is this minus 1 over x. If I multiply by x, I get minus 1. Q is this thing. If I multiply by x squared, x squared over x minus 1 cubed. Evaluate that at x equals 0, I get 0. So E0 equals 0. Plug it into this formula again. That it says the roots are 0 and 2. Those roots differ by an integer other than 0. So this is a case 2 case, where we can't tell at this point if we'll get 1 or 2 linearly independent Frobenius series solutions. The radius of convergence is the distance from 0 to this singular point, which is 1. So it's 1. So the IC is from 0 to 1, interval of convergence. Another example, this guy. Put it into standard form. I get this for P, this for Q, and 0 is an ordinary point. So we're guaranteed exactly 2 linearly independent power series. The radius of convergence will be 1. Distance from 0 to 1 are minus 1. So here's the interval of convergence, minus 1 to 1. We don't have to mess with additional roots on this case. Here's a fourth example. Let's put it in the standard form. P will be x over x squared, or 1 over x. Q will be this divided by x squared. So singular point is 0. It is regular. There are no other singular points. So the radius of convergence will be infinity. Interval of convergence will be 0 to infinity. Let's see. Here's P. I multiply by x, I get 1. So a sub 0 is 1. Q, if I multiply by x squared, I just get this numerator, which says B. Oh, and then I'm going to let it be, let x go to 0. So the B sub 0 equals minus 1/9. It will be this numerator evaluated at x equals 0. B sub 0 equals minus a 9th. Plug it into our formula, you get this. That all equals 0. You could simplify it and then factor it. And here's our two indicial roots, 1/3 and minus 1/3. They differ by 2/3, which is not an integer. So that is case 1, which means we'll get exactly 2 linearly independent Frobenius series solutions. So I'll do one more, but we're going to end up doing this entire problem. Here's the equation, differential equation. Put it in the standard form. P will be x over x squared, or 1 over x again. Q will be this divided by x squared, this here. So the a sub 0, if I multiply this by x, I get 1. And this, if I multiply by x squared, I get the numerator. If I evaluate that at 0, I get minus a 4. So that's what 0 is. Put that in our formula, quadratic equation, and it says our indicial roots are plus and minus a half. In this case, they differ by an integer other than 0. So that's a case 2 where we don't know at this point if we'll get 1 or 2 for linearly independent Frobenius series solution. Since the only singular point is 0, the radius of convergence is infinity, and the IC will be 0 to infinity. We'll actually solve this equation in another recording. That's how to characterize series solution.